Hello guys, so we are going to continue the discussion with respect to transformations and functions. Already we have discussed about what exactly is a transformation. In this video we are going to discuss about inverse of a function. Now this is also a really important concept. So first of all, we will try to understand the definition, we'll try to understand the mathematical intuition, what is inverse of a function, and then how this is related to data science and where all in data science this will be used. We will be discussing about it. Okay, so let's go ahead and first of all see the definition, and then I will start writing some notations over here. So over here you can see inverse of a function is a function that reverses the effect of the original function. Okay, if you have a function f that maps an element x from set x to an element y in set y, then inverse function f dash f inverse, I can basically say f inverse, this is nothing but this is the inverse of this particular f function. It maps y back to x. Okay, so I hope just by seeing this definition, and if you have already seen the previous video with respect to function, I think you should be able to understand that, right? So here let me just go ahead and write it in some notation. Given a function f, right? So let's say this is f, and this function f, what it does is that it maps every element in x, or it maps an element in x to an element y in set y, right? So that is what is basically written over here. So this is what is the mapping function. So if we have a function, let's say if we have this specific function, then inverse function is nothing but we will be writing f dash, and here our any element of y from set y will be mapping to an element of x in set x, right? So this is just the reverse of this. So I will be having a f dash function, f inverse function, which will be mapping some elements of y to some of the elements in the set x. Okay, so this is what inverse function basically means. Here I also need to write one very important point. For every y belongs to the set y, there is a unique x that belongs to the set x, such that these are some of the condition, such that f of x is equal to y. Okay, now what is f of x is equal to y? F of x is equal to y basically means for every element, right? For every element that is present in this y, which is belonging to the set y, there is a unique x that belongs to the set x, such that f of x is equal to y. Okay, now please remember the specific conditions, because I will try to explain you with multiple examples, and we'll also try to solve some simple examples itself, right? So if I really want to say a function is the inverse of another function, the inverse function, I can go ahead and write inverse function f dash satisfies the following condition. The first condition over here is for all x which belongs to the set x, I can go ahead and write this function as f inverse of y, okay, is equal to y. Okay, we'll understand this, what exactly it is. Right now I'm just writing the definition, and just by seeing the definition also, I hope you will be able to understand. For all y belonging to y, set y, f inverse of f of x will basically give me x. Okay, now what does this basically mean, right? And let's consider this is my set x. Okay, and this is my, I'll create some diagram over here. This is my set y. So this is my set x, this is my set y. Now what does this basically mean? Okay, given a function f, and from this particular function you'll be able to see that It is mapping an element of X from set X to element of to an element Y in set Y, right? And that is how this is denoted. So any element that is probably present over here, let's say this is the element and this is basically mapping to this element, okay? And I may have another element, this is mapping to another element over here. So this mapping is specifically done by a function which is nothing but f of X to Y, right? So this is just like a transformation. Now what does F inverse basically mean is that, and according to the definition, F inverse, it maps the element Y back to X, right? Now for this particular element, if I want to map it back to this element, right? I want to map from here to here. So I can specifically use F inverse, and here the transformation will be from Y to X, okay? So this is what we are specifically doing, right? So it's just like if I'm doing a transformation from one element of X to the other element of Y in this set Y, in order to come back, right, to this original element, I will be using an inverse function. That is what it basically says, right? Now let's think about this. The inverse function satisfies the following condition. Here we are saying F inverse of an element of Y. Okay, so internally see over here, what we have written over here is that F inverse of a element of Y, right? So let's consider that there is an element over here. If I do the F inverse, so it will go and probably find me an X element, right? If I do an F inverse, then once I get my X element, if I still apply on top of that function over here, which is not an inverse, then I will be able to get my element back, that is Y. Right, here we are basically applying the F function. Similarly, for all the Y elements that belongs to Y, we are just first of all applying F of X. F of X is nothing but we are getting an element with respect to Y, right? And then when I apply an inverse, right? When I specifically apply an inverse over here, on top of it, I will be getting an element back that is nothing but X. That is what it basically says, right? So I hope you are able to understand the importance of inverse. I'll not say importance, but at least the definition of inverse. With the help of inverse, we get whatever transformation we have done from X to Y, we can again come back from Y to X with the help of the inverse function. Okay. So here we can also give a very good statement. This conditions imply that applying function, and it is very, very handy topic, guys, and probably in machine learning we'll be extensively using this, okay? The function, and then its inverses will return the original value, okay? Whatever is the original value. So let's read this statement. The condition implies that applying a function and then its inverse will return the original value. Yes, obviously it is returning the original value. Initially I had this, then I got this, then it is returning the original value. Now before I go ahead, I really want to talk about one very important function, which is basically called as an identity function. Okay, what exactly is an identity function? Why do we use an identity function? Okay, so just a small topic over here, and then we will probably continue the discussion, okay, with respect to this inverse function. So first of all, we'll go ahead and define our identity function. Now, identity function is a kind of transformation. Let's say if I go ahead and denote this, let's say I'm going to perform identity on X, and this, what it is going to do is that when we apply identity function on any element of X, this is basically going to give me X, okay? And here we are considering, let's say that A is basically present as an element in X. So I can also denote this as I of X of A is equal to A, right? So that basically means whenever I try to apply any transformation, it can be on vector A, matrices A, you know, and if I'm applying an identity function, I'm going to get the same value. And it is very simple, right? What is an identity function usually, right? If you see an example with respect to identity function, how do we denote it? So let's consider a 2 cross 2 matrix, okay, of an identity function, okay, and I will probably denote this as I, right? So let's consider I over here, and I have 1 0 0 1. Okay, now let's say that I'm going to apply a transformation on a vector 2 comma 3. So when I'm applying this, I'm basically doing some kind of operations over here. So if I just go ahead and calculate IV, right? IV basically means I'm doing a dot product of I and V. So if I have over here 1 0 0 1, right? And if I take 2 comma 3, then here you will be able to see that I will be getting 2 3 only, right? How does the operation take place? 1 multiplied by 2 plus 0 into 3. Finally, we'll be getting 2 3, right? So in short, what is basically happening? Any dot product that we do specifically with respect to that identity matrix or identity function, you should be able to get the same value. Okay, so you can also go ahead and write like this: for a set X, the identity function I of X is defined as, and this is also one type of function transformation only, right? So if I go ahead and write I of X of A, let's consider that this is my set X, and let's say A is one of the element, right? Is equal to A for all A belongs to X. Okay, so A is just an element with respect to X. Here we can specify that Ix is the identity function on the set X. Okay, on the set X, and it maps every element X in X to itself. Now what does this basically mean? It basically means this one only, right? Let's say if this is my space or this is my set, okay, and I have an element X over here, or this is my A element, and this set is nothing but X, and A belongs to X, right? When I apply an identity function, in short, I'm going to get the same value. Okay, I'm going to probably get the same value, right? Same value after we apply an identity function. Okay, the two important properties of identity function, which we also need to keep a note in mind. Okay, so let me go ahead and write the properties of identity function. Properties of identity function. This will all make sense once I give you multiple example. Okay, and we also use a lot of identity functions in various algorithms for some purpose. Okay, so first one is that the properties of identity function is something called as preservation. Preservation basically means here you know that identity function does not alter any element. So here I can go ahead and write it does not alter any element. Whatever is my vector, whatever is my element, I will get the same element once I do the dot product or once I do the transformation. Okay, so when we say that it does not alter any element, I can basically go ahead and say if X is the domain, then the image of X, under the identity function is X only, right? Under the identity function is X only. Okay, so this is one thing, and that is what I have actually denoted in the above diagram. Okay, now with respect to an identity function, one more very important property that you have is something called as linearity, and I hope we have learned about linear transformation, right? So identity function by default is a linear transformation. Identity function is a linear transformation. So when we say this is a linear transformation, that basically means, again, remember the condition, the origin will be same, the lines will be straight, and here we can basically go ahead and write the two rule, additivity and homogeneity. So when I say identity function is a linear transformation, I can basically go ahead and write I of u plus v is equal to nothing but I of u plus I of v. I hope everybody remembers this, right? This is additivity. The second condition is basically like homogeneity. I of c of u is nothing but c of I of u, which is equal to c of u, right? So this is also basically satisfied, right? How do we identify identity function? Okay, the third topic, the third important point. How do you mention an identity function? Identity matrix, first of all, is specified in this way. Let's say that first of all I take a matrix. It can be an n cross n matrix, right? And it needs to be n cross n matrix. Here all the diagonal elements will be 1. Okay, will be 1 and zeros elsewhere. That is how we specifically denote it. Okay, so here let me just go ahead and denote it. Let's say if I have a 3 cross 3 matrix, then I will be denoting my identity function as 0 1 0 0 0 1, right? So this is basically my 3 cross 3 identity matrix. Okay, I can also define 2 cross 2 identity matrix. Here I can go ahead and write 1 0 0 1. So when I say diagonal elements, these are my diagonal elements, right, with respect to 1. Okay, and one more important thing that you really need to understand is that this identity function, the fourth point over here, the identity function, it's its own inverse. Okay, so the identity function, it's its own inverse. It's its own inverse. And this is also very simple, right? So I can also denote something like this. First of all, if I go ahead and apply a transformation I of x, okay, see, let me just make you understand what this sentence means. The identity function is its own inverse x. If I apply this on x, I will be getting x only. Again, if I go ahead and apply on it, I will again be getting x. So I can basically say that, hey, it is its own inverse. So guys, till here we have understood two important things. What is an inverse function and what is an identity function. Okay. Now, it is always necessary that if I have a function, how do we say that it has an inverse? Okay. So for that, let's go ahead and talk about two important things. One is existence and uniqueness. Okay. Now, what does this important two property talk about? That is what we are going to discuss about. So here, I can go ahead and write a function f has an inverse if and only if it is bijective. Okay. So a function has an inverse if and only if it is bijective. What is bijective basically mean? So bijective satisfies two important properties. One is something called as injective. When I say injective, I can basically say it as 1 to 1. Okay. What is 1 to 1? Here, different elements in the domain map to different elements in codomain. I hope you know what is domain and what is codomain, right? It was explained in the previous videos in this series, right? So different elements in the domain map to different elements in the codomain. Now, if I probably consider domain, this is my domain and my Y set may be the codomain. Okay. This can be codomain, this can be domain. So what we are basically saying over here is that according to this, a function has an inverse if and only if it is bijective. When we say bijective, we need to satisfy two properties. One is injective. Injective basically means 1 to 1. Different elements in domain map to different elements in the codomain. Okay. Like if this is my element in domain and this is my element in codomain. Okay. So every element of domain should map to a different element in codomain. Okay. Something like this. Okay. This is what it is basically saying. Second important thing that you have is something called as surjective. Surjective basically means onto. Okay. So here every element in the codomain is the image is the image of at least one element in the domain. Okay, every element in the codomain is the image of at least one element in the domain. Okay, so here at every element is at least one element, at least the image of one element in the domain. Okay, so this is what subjective is basically. So based on these two conditions, if this satisfies two conditions, I can basically say that a function has an inverse. Okay. Now let me just give you a very basic example that how you can find out a function. Okay, how do you find out an inverse function? So one of the example is something like, I will just take an example with respect to linear function. Let's consider a function over here. F of x is equal to 2x plus 3. Okay, now what is this f of x 2x plus 3? Like for every x element, I will just try to go ahead and find out what is 2x plus 3. And when we say linear function, if you just go ahead and plot this with respect to every x element in, and let's say if x is 1, then this will be nothing but 5. When x is 1, so I'm getting 5, right? Then when x is 2, I will probably get 7. Then when x is 3, I may get probably 9. Then like this, it will go on. So when I say linear, so this is specifically following a straight line, right? So that is the reason we basically say this as linear function. Now, in order to find the inverse for this linear function, and we have to probably see whether this is whether it has an inverse or not. Okay, so we will go ahead and solve the equation. So let's go ahead and take instead of f of x, I will write y is equal to 2x plus 3. Okay, considering f of x is nothing but it is equal to y. Now for x, we will try to solve this problem. So let's go ahead and solve this. Okay, so here I will go ahead and write y is equal to 2x plus 3. And then let me just go ahead and write y is equal to y minus 3. I'll take this over here. I'll get it as 2x. And finally, if I go ahead and calculate x, it is nothing but y minus 3 divided by 2. Okay, so this is for any x value. Okay, if I want to probably compute x, I just need to change this y value and get it. Okay, so here once I get this x, since we are solving the equation, this one for x, right? So after we find this, I can basically go ahead and write the inverse function. The inverse function f dash of y is nothing but y minus 3 by 2, right? So we can specify this in this way, because we are solving this equation for x, for any value of x, right? And my main aim is, see, over here, this particular function, what it is basically doing, if I have some set x, okay, and I have some set y, this x element is basically getting mapped to y, right? This is my domain, this is my codomain by this equation. Now I need to find out a way to come back, right? So what I will do, I will solve this entire equation for getting the element of x. So here I will be writing, I will take this y is equal to 2x plus 3, y minus 3 is equal to 2x, and then for x it is nothing but y minus 3 by 2. So here the function that we are specifically going to apply, right? If I just take this as an example, it is very much simple. Here we are basically writing f of I is equal to 2x plus 3, right? Now if I want to come up with the inverse, so it is nothing but f dash y with respect to y minus 3 is by 2, right? By this, I will be coming back to the same element, and by this, I will be going to a new element in y. Okay. So this is one example. And again, if you really want to again verify it, okay, I will also try to prove it by some verification. Verification basically means how do I verify this? See this. It is very simple. What I am actually doing, I will first of all apply a f inverse function on y. Okay. If I apply this, I should be getting an element in x. And if I apply the function back again, I should be getting the element of y. So here I will go ahead and write what is f inverse of y? It is nothing but y minus 3 by 2. Now when I say y minus 3 by 2, it is again nothing but 2 y minus 3 by 2. Okay. So f is nothing but what is f? 2x plus 3. And I'm considering this as x, right? So here we will go ahead and write 3. Now if I go ahead and expand this, this 2 and 2 will get deducted. I have y minus 3 plus 3, which is nothing but it equal to y. Okay. Second, f inverse f of x is nothing but f inverse. And here, what is f of x? Again, 2x plus 3, which is nothing but 2x plus 3 minus 3, right? 2x plus 3 minus 3 divided by 2, right? So if I probably consider this is just my 2x plus 3, right? Minus 3 by 2, okay? Again, if I probably want to go ahead and solve this, okay, if you just go ahead and solve this, it will be nothing but it will be equal to x, right? So here, in short, when I do this, it is basically saying from y I'm going to x element, and again after applying a function I'm coming back to y. And here initially when I add an x element, when I'm applying this function, it goes to y, it gets mapped to y, it gets transformed to y, and again when I apply an inverse, I'm going to get x. So this basically proves both the scenario over here, right? And this is how you basically calculate inverse for just a set of elements like x, okay? But we also need to see that how do we calculate the inverse for matrices, okay? That we will do in the upcoming videos, okay? Similarly, you can apply this to quadratic equation. You can apply to different kinds of equation itself, okay? Now, the most important part which I will be discussing is about applications. Where or applications we specifically use this in data science, because mathematical intuition, you got it right. I hope everybody is able to understand what exactly is function, what exactly is an inverse function, you know. But these all are nothing but these are kind of transformation techniques itself. Now in the next video, I will go ahead and detail about each and every application about this particular transformation. That is what we are basically going to discuss about in the next video. So yes, this was it from my side. I will see you all in the next video. Thank you.